Last time, we talked about using vector and matrix notation to represent electrical circuits. But what if we want to use one physical system to represent another physical system? How do we know when a parallel between two systems exists? The reason we care about this question is that we often use our physical knowledge about one system to reason about another. For instance, we know that mechanical systems can oscillate if damping is low, and from that we might reason that electrical systems can oscillate with low resistance, but only if there is an inductor to play the role that mass would play in a mechanical setting. This skill of translating between mechanical and electrical systems is a key part of how we double-check that solutions we obtain actually make sense. Remember that capacitors are like springs, resistors are like dampers, and inductors are like masses. As an example, let's start with a capacitor-resistor simple circuit. So here we have a capacitor and a resistor that are in the same loop. You probably can guess that the spring damper system, where there's a wall, a spring, a damper connected together, is an analog of this circuit. But in what sense are they equivalent? The answer is in the ODE that represents each one. In the case of the circuit, the ODE is Q dot is equal to -1 over RC times Q. Now, in the case of the mechanical system, X dot is equal to -K over B times X. We think of two physical systems being equivalent when the ODE that describes them is the same, and in this case, they are the same. If we add an external force to the spring damper system here, so we have an external force, what type of electrical system should have an equivalent equation of motion? Once we add a battery to the circuit, the two differential equations are the same again. So here we get plus VB over R, and here we get plus F external over B. Let's say that now we start with a capacitor-inductor circuit. What is the mechanical analog of a capacitor with an inductor in a loop? You probably guess a spring-mass system, a wall with a spring and a mass. These two systems have the same ODE. Q double dot is equal to -1 over LC times Q, and X double dot is equal to -K over M times X. Now they are also the same as this slinky. So horizontally, there's no external force, but there's a mass and a spring. And then if I add an external force or add a battery, they are equivalent to this slinky oscillating in gravity. Another example is the capacitor-resistor-inductor circuit. So now I have a capacitor, a resistor, an inductor, all in a loop. And this is equivalent to a wall with a spring, a damper, both connected to a mass. Now let's say I have a different capacitor-inductor circuit. What is the equivalent mechanical system? So I start with two capacitors. I have inductors on both sides. And then they're connected by a wire that's in the middle. The equivalent mechanical system is a spring and a mass, and then another spring and a mass, but these are disconnected. So the dynamics of the two masses are completely independent of each other. This is not easy to see in the electrical diagram. At least it isn't so easy for me, but it is really easy to think about in the context of the mechanical diagram. With two batteries, this system would be equivalent to two one-mass slinkies like this. Both of these oscillate because they're in gravity. Now, it's also true that if we add a capacitor to the circuit so that we now have three capacitors, we change the dynamics. So if I add a capacitor like this, the question is what mechanical system is equivalent to this circuit? The equivalent mechanical system has two masses and three springs. So now we add a spring in between here. The middle spring couples the dynamics of the mass on the left to the dynamics of the mass on the right. Again, for me, this is much easier to understand in the diagram to the right. Both of these systems are equivalent to this slinky with two masses. What should you remember from today? Analogues between electrical and mechanical systems are a powerful way of gaining intuition and applying the physical knowledge you have about one type of system to the other types of systems that are equivalent.